And now we are going to analyze flow reactors with variable volumetric flow rates. An expression similar to the equation for variable volume batch reactor exists for variable volume flow systems. The total concentration, Ct, at any point in the reactor is the total molar flow rate, Ft, divided by the volumetric flow, which is B. In the gas phase, the total concentration is also found from the gas law, where Ct is equal to the pressure divided by the compressibility factor Z times R times T, but Ct is also equal to Ft divided by B, so Ft divided by B is going to be equal to the pressure P divided by the compressibility factor Z times R, the gas constant, times T, the temperature. If we apply this equation to the entrance of the reactor, we will get Ct0 at the entrance is going to be P0 divided by Z0 R T0. And if we divide the first expression by the second one, we will have that B, the volumetric flow rate at the exit of the reactor, is going to be V0, the volumetric flow rate entering the reactor, times Ft divided by Ft0 times P0 divided by P times T divided by T0. Then the concentration of J, which is Fj divided by B, is going to be Fj divided by B, but B is equal to V0 times Ft and Ft0 times P0 divided by P times T and T0. So at the end, we will have that the concentration of Cj is going to be Ct0 times Fj divided by Ft times P divided by P0 times T0 divided by T. But the molar flow rate is just the sum of the molar flow rate of each of the species in the system. That is, Ft is equal to Fa plus Fb plus Fc plus Fd plus Fi, and so on. Now, let's express the concentration in terms of conversion for gas flow system. We must remember that we want the concentration in terms of conversions to use it in the Levenspiel chart or plot to obtain the volume of the reactor, something that we will use later on. So, the total molar flow rate can be written in terms of conversion as Ft equal Ft0 plus Fa0 times delta times X, and we must remember that delta is the sum of the ratio of the stoichiometric coefficients. So, substituting for Ft in the equation defining the volumetric flow rate B will give us that the volumetric flow rate at the exit of the reactor is going to be V0, the volumetric flow rate at the entrance, time Ft0 plus Fa0 delta X, all that divided by Ft0, and then all that multiplied by V0 divided by P times T and divided by T0. So rearranging terms and recalling that Ya0 delta is epsilon, we will have that B The volumetric flow rate at the exit is going to be V0, the volumetric flow rate entering the reactor, times 1 plus epsilon x times P0 divided by P times T divided by T0. And the concentration of species J is just Cj equal Fj divided by B. So Fj is equal to Fj0 plus nu J Fa0 times X, which is equal to Fa0 times theta J plus nu J times X, where nu J is the stoichiometric coefficient, which is negative for reactant and positive for product, something that we already went through in the competency 2. For example, for the reaction capital A plus the ratio of the coefficients B and A times capital B will give you the ratio of the coefficients C and A times capital C plus the ratio of the coefficients D and A times capital D. Here, nu of A is equal to -1, nu of B is minus B divided by A, nu of C is C divided by A, and nu of D is D divided by A. And theta J is equal to Fj0 divided by Fa0. So, substituting these values for nu and Fj, we will have that Cj is going to be Fa0 times theta J plus nu J times X, all that divided by B0 times 1 plus epsilon X times P0 divided by P times T divided by T0. Rearranging terms, we will have that Cj is going to be Ca0 times delta J plus nu J times X divided by 1 plus epsilon times X, all that multiplied by P and P0 and T in T0. And we must recall that YA0 is equal to FA0 divided by FT0, CA0 is equal to YA0 CT0, and epsilon is equal to YX0 times delta.